So this is the second hour of Physics 1B for October 25th, and now we're going to be talking about paths between states. It's really paths between thermodynamic states. There's a question in chat. I'm going to get to answering that in just a second. Thermodynamic states. Because the path taken is going to matter. All right, so Kelvin says, or Donald says, if we did V2 to V1, our answer would be negative, and the negative would, yes. That is correct, Donald. If we switched V1 and V2, we would have gotten a negative 1728. Exactly. Yep. That's right. So I guess what I was trying to describe before the break was we have to have some way to get back to the original state, but use less energy. Because if we can do that, then we can gain energy every single time, right? But quite simply, yeah, like you say, just flipping these two around, that's not going to work. So this next section is about finding other ways to move between states. All right, so paths between thermodynamic states. So let's talk first about the work done in thermodynamic processes. I keep using this word thermodynamic. I hope it's not confusing you too much. It just means heat in motion, pretty much. I don't know if that's exactly what it means, but it means changes in systems due to changes in thermo, which could be heat, temperature, things like this. All right, so work done in thermodynamic processes. Okay, so the work that we do in a thermodynamic processes depends on the path taken. This shouldn't be too surprising because we can compare what we're about to talk about to something that's really simple. So let's think about Physics 1A, just as an aside, okay? And let's think about a table, and let's think about moving a block across the table. So I've got a block right here. We're looking at the table from the top down, okay? So I've got some block, and it sits right here at some point that I'm going to call A. I'm going to call this point B, and I'm going to call this point C, okay? So what I want you to do is to tell me which of these paths is the work done by friction going to be the greatest. So our goal is to get from A to C, okay? And one path that we could take is this way. We call that path 1, okay? The other path that we could take is we could go from A to B, okay? And then we could go from B to C. And again, remember that we're looking top down on a box, and we're moving the box from point A to point C. But there's two different paths that we're going to take. Along which path is the work done by friction the greatest? Or I should say, the magnitude of the work done by friction. Because you could say it's negative if you want to. Okay, so just the magnitude. Not the sign. Don't worry about the sign. Yeah, which is path 2, right? The answer is path 2, obviously. It's obvious, right? I don't like saying things in physics are obvious very much, but we know for a fact that if I construct a triangle and it's made up like this, that the shortest distance between A and C is definitely going to be less than the distance from A to B than B to C. Is that part obvious? It may not be obvious to a 4-year-old, but I'd hope someone that's like you all that have studied a lot of mathematics understand that AB plus BC has to be greater than AC, right? It's one of the rules for closing a triangle, pretty much. So if it's a longer path, then the work done by friction is greater, right? This is one of the ways that we say that friction is a non-conservative force, because the path you take changes the work done, right? So coming back to thermodynamic systems, the work done also depends on the path taken. But the path in this case is not going to be the path in actual space. It's going to be the path on a PV diagram, okay, where you plot pressure versus volume and you talk about going through different states. So here's an example of that right here, okay? There's really multiple examples. The work done by a system during a transition between two states depends on the path chosen. So this says these paths give options for getting from state 1 to state 2. All right? So we're going from state 1, which is up here in the corner, down to state 2, right? And there are 3 different options, B, C, and D, okay? One possible way would be to first increase the volume from V1 to V2 at constant pressure along this line, and then to decrease the pressure from decrease the pressure from P. I think it caught up. This is supposed to be P1. It cut off when I copy pasted it. Decrease the pressure from P1 to P2 at constant volume. So we would have gone from 1 to 3 and then down to 2, okay? And the work done would be this entire area, right? Remember from what we did before break, the work done is basically the area under the curve or the integral of PdV, which I'm just going to say is the area under the PV curve, right? The area. So we can see that if we first increase the volume from V1 to V2 at constant pressure, and then we decrease the pressure once we've gotten to that larger volume down to pressure 2, now the work that's done by the system, right, is going to be this total area right here. Quite a bit of work, right? Quite a bit of work. You might also notice that there is no work done from path 3 to 2. So the work done from 3 to 2, can you see that this is equal to 0? Because you would take the area under the curve from here to here. It's a line that goes straight up and down. So what's the area under that curve? It's 0, right? Can you all see that? So all of the work is actually done by the gas just in the increase in volume. And somehow, however this decrease in pressure is occurring, there's no work being done. All right. Another possibility was we could do that pressure decrease first. Notice now that if we first decrease the pressure from P1 to P2 at constant volume, and then we increase the volume from V1 to V2, we get a remarkably smaller area, right? So this is much less work than B. And remember that this is work we're getting out of the system. You know what I mean? It's not quite like friction, where with friction, that work that's done by friction, it's really hard to get it back, you know? It's really hard to get it back. Think about, you're in your car, right? And you're driving in your car, and you're driving along the road, you've got some kinetic energy, right? And you see a stop sign ahead, so you start to slow down. You slow down by pushing the brakes, which means the brakes exert a friction force on your tires, or on the brake pads, but that friction force causes the car to slow down. And now all that energy the car had while it was driving, all that kinetic energy, it's now basically gone, right? You can't take the heat that was created in the brake pads and turn them back into energy to drive the car. You know what I mean? Is what I'm saying clear? You have a car driving along, has kinetic energy. You push the brakes. How do you get the kinetic energy back for the car? Well, you have to put energy into the car again, right? By pushing the gas. It's very hard to get that the energy lost by friction back. But what we're talking about here is the work done by the system. And path B clearly produces more work than path C, right? So if you were designing a system and you wanted to get energy out of the gas, you wanted to make the gas do work for you, then you would definitely prefer path B if you could. Does that make sense? Because path B would quite simply produce way more work. Are you all on board with what I'm talking about? It's so hard when I can't see people nodding or like look at faces, but do you all understand where we're at so far? I will say that I think it was in this class. It was either in this class or 1C that I think people were telling me that newer model BMWs have actually found a way to kind of like harness some of the energy of the braking force. Was that this class that someone was telling me that? Maybe it was my night class. It could have been my night class. I don't know anything about this. Someone just told me that, so I have to take their word for it. But they claim that they have some technology where they do reuse some of the heat that's lost in the breaking process somehow. That is probably exactly what it is, Donald. It's called regenerative braking. We should talk more about that. That sounds extremely interesting. Maybe if we have a little time at the end, we'll go look that up and talk about what it means. Maybe you can tell us about it, Donald. Tell us about it. What do you know about regenerative braking? While you're typing that, I'm going to go ahead and go on to D here. So 3 different paths, right? So path B got the most work. Path B, very tiny amount of work. And then the other possibility is just what we did in the last problem, the isothermal expansion. We increase the volume from V1 to V2 while decreasing the pressure from P1 to V2. This would be like just normal isothermal expansion. And then the work done is this area here, which is going to be somewhere kind of in between the two. Now, just because part B gives the most work, it doesn't mean that it's going to be the best way to do things, which we're going to find out pretty soon, because sometimes you just need natural processes. And maybe this process is kind of unnatural. Okay, maybe B and C are both unnatural. I don't know. But there's certainly ways we could make it happen. All right. So that's talking about the work that's done in a... okay, let's read what it says. Some of the energy from braking goes back into the battery to give you extra range. When you go downhill, an electric car can gain mileage instead of losing because of that regenerative braking. Ah, cool. Because it's just rolling. But it's not really rolling because you're probably applying brakes. And basically what you can do is you can use that to recharge the battery. That's neat. That is really clever. That is really clever. Okay. Even if it only increases the efficiency by a tiny amount, that's huge because anytime you can gain more efficiency or lose less energy is always great. Alrighty, so that is that. Just the biggest thing to take away from this is that the work done does not just depend on the initial and final states of the system. It depends on the path taken. And when I say path, I mean path through a PV diagram. Okay. The biggest takeaway from this is work done by the gas depends on the path, not the endpoints. In your PV diagrams. Okay? That's the big takeaway from this. All right. The next thing we want to talk about, which is what this picture is for. Oh, wait a second. Any questions about what we just described? Okay. So now we want to talk about the heat added. In thermodynamic processes. Okay, so for this one, again, the heat that gets added is going to depend upon the path taken as well. And the way that we're going to talk about this is through this picture right here. Okay, let's see if we can make it a little bit bigger. So we're going to consider 2 different systems that are going to take our gas from 2 liters to 5 liters, okay? So okay, so the gas goes from V1 to V2 of 2 liters to 5 liters at a constant temperature of 300 Kelvin, okay? And the idea will be that we're going to take the gas between these 2 states, okay? This is state 1, this is state 2. And we're going to say that they start and end in the same state, okay? But we're going to find that in each case, the work done and the heat transfer is going to be different, okay? So state 1 for the first system is going to be, we take a gas, it's at 300 Kelvin, right? And we connect it up to a heat reservoir that is also at 300 Kelvin, and we're going to consider this a heat reservoir that will always maintain a constant temperature for the gas, okay? So we have some heat reservoir here that is going to make it so that the gas maintains its temperature at 300 Kelvin. This could be something as simple as like a hot plate that's always adding heat into the system. Actually, that doesn't even make sense. No, I guess it could be. So this could be a hot plate. It keeps the gas right at 300 Kelvin, right? But it could also just be the air around the gas. Okay. Could also just be the air around the gas. Okay. So in A, we have a slow, controlled isothermal expansion of a gas from an initial state 1 to a final state 2 with the same temperature but lower pressure. So the pressure is changing in this case. Okay. Pressure goes down. But we add heat to the system here, and we do so in a very slow way so that the gas expands from 2 liters up to 5 liters. Okay? Does that make sense? In this case, there is heat coming in. So heat comes in here, which means that Q is positive, and the system does work. So what's the sign of the work going to be? I mean, you can see what it says right here. But because it expands, the work done on the system, the work done here, is also positive. Okay? Does that process make sense? I kind of want to read the way that the book describes this to make sure that I'm hitting on all the details here. So I'm gonna read this for you. So it says, suppose we want to change the volume of a certain quantity of an ideal gas from 2 liters to 5 liters while keeping the temperature constant at 300 Kelvin. The figure shows 2 different ways to do this. In the first figure, the gas is contained in a cylinder with a piston with an initial volume of 2 liters. We let the gas expand slowly, supplying heat from the electric heater to keep the temperature at 300 K until the gas reaches a final volume of 5 liters. The gas absorbs a definite amount of heat in this thermal process. So in this case, kind of the reason why the gas is expanding is because it's effectively not allowed to cool. So we're adding temperature, we're adding heat, it causes it to expand, it does positive work, it takes in heat, right? Both of those are positive, okay? The other possibility, and this one is seemingly the same idea, but is a little bit different. So we completely insulate the gas so that it can't exchange energy with its surroundings. And then we have a breakable partition here. Imagine just some type of, I always think about like a piece of tissue paper or something like that. Imagine you try to contain a gas with just a tissue paper here or something like that. And above that, you have a vacuum. So naturally, the gas is going to want to expand, break the partition, and expand into the surroundings here. Okay? Now, in B, which we'll talk about more over here, let's use a different color. So in B, insulation, it's an insulated system, which means that Q is equal to 0. That is to say that there's no heat that can come in and there's no heat that can go out because it's insulated. We're going to assume it's perfectly insulated, which is impossible, but we're kind of doing like thought experiments here. In addition, that there's no piston to move. So work is also equal to 0. So we call this type of expansion here, we call this, I just noticed that part of this is cut off. We go like that. Breakable partition. We call this the free expansion of an ideal gas. We're going to see this show up again. Does it have to be an ideal gas? I think it does. But we call that the free expansion. Okay. So what do we take away from this? We have 2 different paths, right, that take us from state 1 to state 2. 2 different paths that take us from state 1 to state 2. Okay. One of them is a very controlled and slow expansion that occurs in the first one. The second is a very rapid and almost instantaneous expansion, or rapid and uncontrolled, as they say. But we end up in the same state in both cases. Okay? We end up in the same state in both cases. In one case, we've added energy to the system, and the system has done work. In the other case, we haven't added any energy, and the system hasn't done any work, right? So it turns out that the heat added depends on the path you take. So I'm just going to put that up here at the very top. I'll put it somewhere. I'll put it right in the middle, I'll just say. Heat added to our gas depends on path taken. You can get between two different states that are exactly the same, but the heat added is different in each case. The work done is different in each case. So the next thing to ask then is, what does this mean for the energy of the gas? Or let's say that, let's say we call it the quantity of heat or something stupid like this. Does that make sense? Let's say that, let's put some numbers to this. Let's say we add 1,000 joules, okay? Let's say that that's how much heat was added here, was 1,000 joules. That's how much heat was added. Does that mean that this gas has more total heat than this gas? Does that even make sense? Does the question make sense? Which gas has more heat inside of it? Is it the one that had heat added to it, or is it the one that was insulated? Which one has more total heat? More quantity of heat. What does that even mean? What is quantity of heat? The one with the heat added? That'd be the natural thing you want to say, right? More quantity of heat. So the key thing to understand here is that heat is transferred. It's always transferred. It's never... Like, we can quantify how much heat gets transferred between two systems, but the concept of quantity of heat is a bad way to talk about what happens inside of the system. Instead, what we're going to do is we're going to say that that this is a meaningless question, basically. That talking about quantity of heat is just, this is a really bad way to talk about what's happening with the gas. Instead, what we want to do is we want to turn this into something that's more general, which we're going to call internal energy. This is going to be another variable. We're going to use the symbol U for this, okay? And what I'm going to try to argue is that the internal energy of this is going to be the same as the internal energy of this. They will have exactly the same internal energy. The internal energy is only going to depend upon pressure, volume, temperature, number of moles maybe, and that's all that it can depend on. That's all that can, and maybe some constants, okay? So that's exactly where we're going next. Let's see how much time we have left. We have a decent amount of time left. I got this question here. I want to ask this question real quick. This is this section, right? But we need the picture up here. Okay, let's ask this question. We got to go back to these pictures, though. Okay, so look at these 4 pictures here. I need to make this bigger so you can actually read it. Let me just... Can I move all this stuff down? Will it let me do that? Yips. All right, let me zoom out. Apologize. Just give me a second. Should have worked. It did. Now I can make this bigger. All right. So let's go back up here. I may have to make it a little bit smaller. Okay, so looking at these pictures here. So This says, this is the question. I want you all to try to think about this, and you're going to answer in the chat. The system described in figure 19.7a undergoes 4 different thermodynamic processes. Each process is represented by a PV diagram as a straight line from the initial state to the final state. So it says each process is represented in a PV diagram as a straight line from the initial state to the final state. These processes are different from those shown in the PV diagrams, okay? But the numbers are the same. So 1, 3, 4, and 2, these are all the same, okay? So really, we just have to look at this picture right here. The question is to rank the processes in order of the amount of work done by the system from the most positive to the most negative. And your options are 1 to 2, 2 to 1, 3 to 4, and 4 to 3. So you want to rank these from the most positive to the most negative. And again, it's saying that the system described, each process is going to be a straight line from the initial state to the final state. So 1 to 2 is going to be a line that goes straight from 1 down to 2, like that. And 2 to 1 will be the same line, but it goes back that way. 3 to 4, 3 to 4 would be like this, right? And 4 to 3 would be like that, okay? Can you all think about that? I'll give you a minute or two. What would be the most positive and what would be the most negative? Take a minute and try to answer that. As soon as you get an answer, you can feel free to go ahead and write it in the chat. It shouldn't take super long. Okay, go ahead and put an answer in the chat. Don't worry about what other people put. Just put your own personal answer. The whole point of stuff like this is just to take some time to think about it so you can gauge for yourself if you understand what we're talking about. Go ahead and put your answer in because we're kind of like want to kind of move along. So just push enter. Put your answer in there. I think there are multiple correct answers in this case, so don't be afraid to get it wrong. Yeah, I mean, you can write it as 1 equals 4 is greater than 2 equals 3, which I think is the correct answer. Seems like most people are on the right track. Most people said everyone tends to agree that 1 is the greatest, and that's true. But if you think about it, this one and this one are going to be equal to each other. So I would write it as I is equal to IV is greater than, the other two are the same as well. Shall I agree? That's how I would rank them. Because 1 to 2 is a straight line from here to here, which makes a trapezoid, and then 4 to 3 is a straight line from here to here, which makes the same It's like a mirror image of the first trapezoid, so they're going to have the same area under the curve. Unless I'm crazy. They are, right? It's a rectangle. They have to, right? Yeah, they do. And then the other two are negative. So 2 is the one that goes from 2 to 1, which is going to be a rectangle or trapezoid that goes from there to there, and you take that area. And then 3 to 4 is going to be a line from here to here, and then you take that area, which is going to be exactly the same. Okay, just a little quick quiz to kind of test our understanding of this. So let's finish up class today by talking about internal energy of a system. So internal energy, as I said, is a better way of talking about the quantity of heat within the system. It's not at all about quantity of heat. It's really about a way to describe how much, that's what the word says, internal energy. So we're going to describe internal energy as the energy that arises from all of the kinetic energies of the molecules. We're going to use U to represent this. This is going to be just kind of a sum of all kinetic and potential energies associated with the molecules. So what could this be? So the kinetic energies, we know what that is, right? That's like the translational motion of the molecules. They have velocity, so you have 1/2 mv squared from that. And we know that if a gas has a temperature T, that the kinetic energy of a single molecule on average is going to be 3/2 kT, right? So it's going to be related to that, obviously. But also possibly potential energy. So the molecules themselves may have binding energies that may show up as internal energy. There also may be interactions between the molecules themselves, and those may show up as potential energy. We're going to use the symbol U to represent the internal energy of a system, okay? And it's going to be heavily tied to things like temperature, but importantly, it's just something like this. It's a macroscopic variable, so we don't need to know anything about the individual kinetic energies and potential energies to actually find what this is, but we should be able to find it in some way, okay? Often what we're going to be talking about is change in internal energy, and this is going to be defined as basically the, kind of moving from one state to another. I know that in Physics 1A, we use the symbol U for... we use the symbol U to represent potential energy, and I know that's kind of confusing. Something just got to kind of get used to with physics, that there's only so many symbols in the alphabet, and they like to use a lot of them over and over again. Anyway, so on the left right here, we talk about the ways in which the total energy of a system can change. And it turns out that there's a way to connect change in energy, okay, to heat added and to work done. Okay, and it's just like this. All you do is you say the change in internal energy of a system should be equal to the amount of work that's added to the system, right? Sorry, the amount of heat that's added to the system minus the work done by the system, okay? So this is the heat added or taken away. Remember that when heat is added to the system, it's positive, and when heat is removed from the system, it's negative. Okay? And then this is the work done by the system. There's this kind of weird... There's this kind of weird thing where it's like Q is the heat that comes in and W is the work done. That's why the negative sign shows up here, because the work done by the system is done on its surroundings, so that's energy that goes out of the system. And heat added is just, the amount of energy that comes in. And so we're going to define the change in internal energy of the system to be equal to this. Change in internal energy is going to be heat added minus the work done. Okay? Shown over here a couple of examples. If more heat is added to the system than the system does work, then the internal energy of the system is going to increase. So suppose I have 150 joules of energy 150 joules of heat that comes into the system. There, that's off the thing. If I have 150 joules of heat that comes in, and then my system does 100 joules of work on the environment, then the internal energy of the system is going to increase by 50 joules. Okay? If more heat flows out of the system, then work is done. So if negative 150 joules of heat flows out of the system, and the system, this happens because work is done on the system, let's say, then you end up getting Q minus W. So what do you get? Negative 150 minus negative 100 is going to be negative 50. So now the system has, its internal energy has gone down. What does that mean? That means the particles are moving a little bit slower, pretty much. I think it's easiest to think about internal energy as being directly related to the sum of all the kinetic energy of the particles. I think it's the easiest thing to think about. Potential energy just means there's some type of internal interactions that are occurring, but yeah. Anyway, so in this case, the energy of the system would go down because more heat comes out and there's not enough work put into it. There's also the possibility that the heat added to the system is exactly equal to the work done by the system, which is going to lead to the internal energy of the system being unchanged, right? So if 150 joules comes in and the system does exactly 150 joules of work, then the change in internal energy is 0. I will say that it is very unlikely we're going to see this very frequently. This is not a very natural thing to happen. It's usually the case that all of the heat that goes in doesn't automatically get converted into work. That's going to be a more rare case, I believe, if I remember correctly, thinking ahead. Okay. So here's the thing that's really cool. First of all, this one has a name. We call this the first law of thermodynamics. You may remember back to, I think the first day we talked about thermo, we talked about the 0th law of thermodynamics. The 0th law stated that when you have three bodies, A, B, and C, if body A is in thermal equilibrium with C and body B is in thermal equilibrium with C, then that means that body A and body B are in thermal equilibrium with each other. That's the 0th law of thermodynamics. It basically just defines what temperature is. Okay. Now we have the first law. And this law is really just a restatement of conservation of energy, because heat added is a type of energy. Work done is measured in joules, so it's related to energy. And then internal energy is this new concept that we're introducing now. And, right, so it's really just a restatement of conservation of energy, is what this is saying here. Especially because change in internal energy is directly related to these two quantities, right? All right, so we've got this definition, and now we want to think about what we talked about in the last section. So in the last section, we looked at, let's see if I can get both of these on the same page here with this. So here's our equation, right? Q minus W. Just keep that in mind. Change in internal energy is Q minus W, right? All right. The question is, as we move from state 1 to state 2, is it possible to imagine that we have the same change in from U1 to U2, from U1 to U2? Is it possible? Let's think about it. So, in case A, work done was positive, Q was positive, right? Work done was positive and Q was positive, right? So it's possible, one possibility, right, is that because we did this process so incredibly slowly, remember if you read what it says carefully, slow, controlled isothermal expansion of a gas from an initial state 1 to a final state 2, then it's possible that the work, is this how we want to do it? I don't know. Anyway, it's possible that work is equal to Q in this case. And if that's the case, then I think that U1 and U2 would be related to each other. And in the second case, work is equal to 0 and Q is equal to 0. So that almost implies, if we look at our equation, delta U is Q minus W, right? So if Q is 0 and W is 0, then what does delta U have to be? If this is 0 and this is 0, then delta U has to be 0, right? So in this case, delta U would just be equal to 0. So it's conceivable then, right, that if in the first case W is equal to Q, then also delta U would also be equal to 0 here, right? So it's possible that U1 and U2 are the same in both of these cases. Just something to think about. Okay. Let's look at some of these diagrams that are supposed to help you understand this. All right. Let's put it all together too. So what did we say in the last section? We said that we talked about the paths between thermodynamic states, right? We said the work done in thermodynamic processes depends on the path taken, right? Path taken changes completely work done, right? For heat added, we got the exact same result. The heat added depends on the path taken, right? So work done and heat added depend on path taken. So now we get down to internal energy. So the question would be, if Q depends on the path taken and W depends on the path taken, what about change in internal energy? Okay. And the interesting thing about this is that experiments show that while heat added and work done depend on the path taken, delta U, or the change in internal energy, does not. Okay? During any thermodynamic process. So that is a really powerful idea, if you think about it. Even though this and this might depend on the path you take, this is going to be constant. We're going to use that a lot in this class to do some proofs and things. So just, keep this in mind. Well, heat added is going to depend on path. Work done depends on path. Delta U does not. The combination of these two will not. Okay. All right. So a couple examples of this that the book gives are here and here. So we'll use this one with exercise first, then we'll look at this one too. So let's read this one. So here we have a woman that's doing push-ups or some type of exercises. And it says, your body is a thermodynamic system. When you exercise, your body does work. Let's think about that. I want to think about this without actually looking at what it says. What does that mean? If your body does work, is W positive or negative then? So you do a push-up. I'll leave it on the screen here. Just think about it. You do a push-up. You do work on your surroundings. Is W positive or negative? If you do a push-up or a pull-up or something like that. Or like lift some weights. Is the work done positive or negative? It's positive, right? You're doing work on your environment, right? Okay. Yep. It says you lift your body as a whole in a push-up. Work is greater than 0. Your body also warms up during exercise. You all agree with that statement? We all warm up when we exercise, right? You go out and you start running. Your body heats up. You start sweating to cool down. That's obvious, right? So our body warms up. That happens, and then by perspiration and other means, the body rids itself of heat. Okay, and if you think about it, we're not taking in heat when we do exercises, right? We're not taking in heat. We're trying to get rid of the heat that we've produced, right? By doing the exercises, our body heats up. That heat didn't come from the environment, right? It came from inside of our body. So as a result, when the body tries to get rid of this heat, which it's constantly going to be doing while you're exercising, right? Let's say you're running on a treadmill, you start to sweat, your body warms up. That sweat has the effect of helping to cool your body. And that means that since we're cooling the body, right, Q has to be negative, right? Heat is going to be leaving our system when we're exercising. Would you all agree with that statement? So what's happening here is that this person is doing work, which means work is greater than 0, but heat is escaping the body. So Q is less than 0. Heat is going out, right? And heat out corresponds to Q less than 0. Everyone down with that idea? I know this stuff gets really complicated. The signs of this stuff is actually probably the trickiest part, in my opinion. Okay, so what does that mean about Q minus W? Okay, so if I have Q that's less than 0, right, and I have W that's greater than 0, right, then delta U, which is equal to, what is it, Q minus W? I always forget. I have to look. Yeah, it's Q minus W. Okay. What's the sign of Q minus W going to be then? This is basically like negative 100, right? Let's say Q is negative 100 joules, and let's say W is, it doesn't matter what I pick. I can pick 3,000, doesn't really matter. Then delta U is negative, right? It's guaranteed to be negative in this case. Can you all see that? No matter what, delta U, guaranteed to be negative. It does not matter what I pick for Q and W, because they are both because W is positive, but it shows up with a negative sign in this equation, right? That means that you're always going to get a negative sign here, right? Okay, so it says since Q is negative and W is positive, delta U, which is equal to Q minus W, is guaranteed to be less than 0, delta U is negative, and the body's internal energy decreases. It says that's why exercise helps, because you lose weight. It uses up some of the internal energy stored in your body in the form of fat. I think you all knew that when you exercise, you burn calories, right? Or you burn fat. Burning calories is a lot easier than burning fat. But yeah, I mean, like when you're burning calories is a measurement of energy, right? You're reducing the internal energy of your system by destroying some of the things that have stored energy in them. This is where, I want to go back real quick here. Remember that internal energy was the sum of all kinetic and the potential energies of molecules, right? Stored up in fat molecules, for example, right? Or when you eat carbohydrates or something like that, you have energy inside of those molecules. And we're effectively burning them or sending them out of our body, effectively, by doing this process, okay? So this is a change in energy within our internal system that does not relate to kinetic energy, right? When we talk about gas molecules and we talk about their energies, we talk about kinetic energy. We talk about like a molecule of fat in your body. It has stored energy, just like a battery has stored energy, and we're using that energy up, and once we use the energy up, it allows us to lose some weight, right? Okay, so because the internal energy of our system goes down, our mass goes down, effectively, because we're burning that energy. Does that make sense to everyone? Okay, now here's the last part that's supposed to help you understand not only the first law of thermodynamics, but also to understand why it is that the change in internal energy does not depend on the path taken, okay? So if you, oh man, we are way over time, aren't we? Wait, are we? What time do we stop in this class? Oh no. We go till like 50 after, right? We have like 10 more minutes, yeah. Got thrown off. Okay, perfect. That means the last break we took was actually just the right time. So let's think about a coffee cup. The internal energy of a cup of coffee depends on just its thermodynamic state. How much water is there? That would be like number of moles. And also how much coffee does it contain, right? What is its temperature? And that's pretty much it, right? If we're talking about the energy inside of a coffee cup, what else could it depend on other than just how much do we have and what is its temperature? It does not depend on the history of the coffee, how it was prepared, where the coffee grounds are from, who made the coffee, whether you bought it at Starbucks or McDonald's or Pete's or something. It doesn't matter how it got there, right? It just has some internal energy, something that we call internal energy, right? And it can't possibly depend on whether it was warmed and then cooled, or whether it was put into a freezer and then warmed up again. You know what I mean? It doesn't matter. Whatever its current temperature is, whatever its current size is, those are the things that are going to determine how much internal energy you have in the coffee. And that's why you could say that even though experiments show that while Q and W depend on the path taken, the change in internal energy does not, you'd say, well, that's obvious, because if internal energy really is something about the sum of all the kinetic and potential energies of the molecules, yeah, right, it's not going to have any effect on the internal energy. Well, I mean, yeah, no, it would, right, Troy? Because now there's cinnamon molecules in there. So, I mean, if you added cinnamon to this, it probably would change the internal energy, right? But, you know what I mean? But in and of itself, if we just look at a single cup of coffee, its internal energy has to be a number. And it can't be different whether the coffee came from being frozen and then warmed up, or whether the coffee had just been sitting out on the table for a while and you put it back in the microwave. It doesn't matter. It doesn't matter how it got to that temperature. It doesn't care. It just has some energy, right? And if you think about the way we understand energy, right, in the sense of conservation of energy, which is one of the big ideas of all of physics, right? If I look at a certain system and I tell you I have a cup of coffee, it's an 8-ounce cup of coffee, and it has a temperature of, let's say, 300 Kelvin or something like that. Those things by itself should be able to tell you how much energy is there. And, if you need more information, then where is that information going to come from? Wynn says, I guess that's why cold weather makes hot foods taste better, because it gives us more energy. I mean, I can't disagree that when it's cold outside, like it's pretty cold today, at least where I live. Yeah, I mean, hot soup, things like pho sound really good on hot days, right? Or on cold days, sorry. Whereas stuff like ice cream sounds really good on a hot day, or, cold water, ice water, stuff like that. So I think that makes sense. It does make a little bit of sense that if you warm your body up, that's going to, yeah. Okay. No more things down here. The next thing we're going to be talking about is cyclical processes in isolated systems. Okay. So this is something that I was kind of hinting at earlier. Okay, so since internal energy is not dependent on the path that you take, when you do a cyclical process, right? A cyclical process is going to be that you take a system from one state, so state 1, over to some other states. Maybe you can call this one state 2. But then you come back to the original state 1, okay? And it's cyclical, so the idea is that we're going to be repeating this process over and over again, right? Now, the interesting thing that happens here is that if I know the energy at state 1, I call it U1, then once I come back around to this process right here and I come back to the original state, then the change in energy, right, which is normally defined as going from, state, is going to be something like U1 minus U1. Does that make sense? If I start at this point right here, some pressure, volume, temperature, right, I take it to some state 2, and then I cool it back down to the original state, my total change in energy for a cyclical process, because you start in the same state as you end in, should be equal to 0. Does that seem reasonable to everyone? A really simple example to compare this to is, instead of thinking about internal energy, let's think about height above the ground. So if I take this object from here, it's got some elevation, and I move it up, and then I lower it back down to the same height. What's the change in height total? It's 0, right? Think about a pendulum. A pendulum that starts, like, let's say here, and it swings from there back to the original position. The change in height is 0, right? Or when it goes from there over to there, the change in height is 0 as well. So cyclical process, and when I think cyclical, I start to think about things like pendulums, right? Because pendulums basically oscillate back and forth and back and forth and back and forth, and they kind of repeat themselves for long periods of time until they run out of energy, right? So when I think cyclical, I'm thinking of stuff like that. Or simple harmonic motion, where you have an object that's oscillating back and forth and back and forth and back and forth. So if delta U is equal to U1 minus U2, and we also know that delta U is equivalently equal to Q minus W, this is the first law of thermodynamics, right? Then we can state that, what's the relation between Q and W then in a cyclical process? We start here and we get back to here, and delta U is 0, and I tell you delta U is equal to Q minus W. What's the relationship between Q and W now going to be? That's right. Q is now equal to W. That means that any energy we add to the system should be equal to the work that comes out of the system, right? Does that make sense? Okay. All right. Another possibility would be is if you have an isolated system, okay? If you have an isolated system, what's the change then? Let's see. So this would be this is for a non-isolated system. So this is something that's actually connected to its environment. So let's talk about what happens in an isolated system. This is a system that cannot exchange heat with its surroundings. Okay? An isolated system can't exchange heat and can't do work on its surroundings. So in an isolated system, if it can't exchange heat, then Q has to be equal to 0. And if it can't do work, W has to be equal to 0. So everything is equal to 0 for the isolated system. Change in internal energy. Again, these are, in both cases, we're talking about cyclical processes, though, specifically. All right. All right. So there's a picture that's associated with, but I didn't copy it down unless I'm crazy. No, I don't think I have. I guess I didn't think we would get this far today. So I'm going to go grab it from the other notes. I apologize. I'll zoom back in. Underestimated how much we would do today. Did I? Because I already copied all this stuff over. Oh, it's just really far down. This one be 1376. It must just be really far down here. There it is. There we go. Maybe we'll have time to do one of these problems too, hopefully. Okay. Zoom back in. Okay, so here's an example of a cyclical process. Let me put this to where it doesn't get cut off by anything there. I gotta do it a little bit. That looks fine. Okay, so every day your body goes through a cyclic thermodynamic process like this one. Heat Q is added by metabolizing food, okay? And your body does work in breathing, walking, and other activities. And if you return to the same state at the end of the day, Q is equal to W, and the net change in your internal energy is 0. So let's go through the process. Let's start from here. So you sleep for 8 hours, and then you eat breakfast. So during the eating process, you can see that heat comes into your system in the form of food. And then there's some work that's done here as well, because the process of eating, actually, you have to do work to eat food, right? Okay. And then you go to work. Now, during the morning work hours, you're not taking any heat from the environment. You're not adding food. You're not eating food or anything like that. So we're going to say that during that work time, you're going to do some work. In this case, it's saying you're going to do about 4.3 million joules of work, or 4.3 megajoules of work. So then you go to work. So you go to lunch, you eat some food, you replenish some more energy by eating 5 megajoules here. And then, of course, that takes some energy as well. You can see it's like the same amount of work that's done here to eat the food. And then you work in the afternoon, which means that you do 4.3 million joules of work, eat dinner, get some more food in your system. That takes a little work. You do some exercise. You study, watch TV. Somehow studying and watching TV, in their assumption, is going to burn as much energy as working. I don't know if that's true or not, but whatever. But then they're saying that basically that if you total up all the Qs here, all the food that you ate, which is 5 plus 5 plus 6.5, so that would be 16.5 megajoules, and then you total up all the work that you've done in their little kind of hypothetical experiment here, then it's saying now delta U is equal to 0. In this process, if you did this every day for the rest of your life, let's say, then I guess I can ask a question. What would happen to your weight if you did this process? Would your weight stay the same? Would it increase? Would it decrease? Would you get fatter? Would you get skinnier? Or it would remain the same, right? Because as we said earlier, you're only going to burn calories or burn fat if delta U is negative, right? You have to decrease your internal energy if you want to lose weight, right? It is true, Troy, that it's possible that your weight might fluctuate a little bit, but on average, it's not going to change very much in this case, right? So that tells you that if you want to actually lose weight, you're going to have to do more work than what they're describing here. Although I will say that if you exercise for 1 hour a day and you eat moderate amounts of food, you will absolutely lose weight if you're trying to, until you get down to a balance. But okay, so that's an example of a cyclical process, right? Because delta U is equal to 0. The amount of heat that came into your system was equal to the amount of work that was done to your system, so it's a net 0 change, and that's an example of a cyclical process. I think we can do some problems now. Let's see how many we can do in 0 minutes. We have no time. Can we do one problem, though, so we can So we can at least say we did at least one. All right, we did one problem earlier, but we really should have done all of these. All right, so it says working off your dessert. You propose to climb several flights of stairs to work off the energy you took in by eating a 900-calorie hot fudge sundae. How high must you climb? Assume your mass is 60 kilograms. Okay, only one new equation now. If you think about it, the only new equation we have is that delta U is equal to Q minus W. 200. It's 900 calories. A lot of calories. Yeah, I guess so. Okay, so we want to burn off 900 calories, right? It says you should propose to climb several flights of stairs to work off the energy you took in by eating 900 calories of a hot fudge sundae. How high must you climb? Assume that your mass is 60 kilograms. All right, so what is 900 calories going to be in this case? Is it going to be delta U? Is it going to be Q? Or is it going to be W? Q. That's the energy we took in, right? So Q is 900 calories, but we need to convert that into, let's convert it into joules. So there are, it's in a food calorie, this should really be a capital calorie. This should be a capital C. In a food calorie, I believe there's 4186 joules for 1 calorie. So we can convert that. So we get, I want to make sure I use the same number the book uses. They use 4190 here. Yeah, that's what they use. Okay. So this is 3.767 times 10 to the 6th joules. So that's Q. Okay, so we've got Q, and then it says how high do you have to climb? So how are we going to deal with this? Is that going to show up as the change in internal energy, or is it going to show up as the work? How high we have to climb, is that going to be the work we do? It's going to be work, right? Now, what we could say, I think, is that the work done should be equal to the change in potential energy. It's probably the easiest thing to say. And that means it's going to be equal to mg times whatever the height that we climb to is. Does that seem reasonable? Now, what does delta U need to be equal to in this case? Do we want to lose weight? Do we want to gain weight? Or do we want our weight to stay the same? Right? So this means weight is the same. So we want to basically just burn off all that we just ate, pretty much, right? All right. So all we need to do is basically say delta U is equal to Q minus W, but this is 0. So that means that Q is equal to W. So the amount of Q that we got is going to be equal to mgh, which means that H is equal to Q divided by mg. So if we just take 3.767 times 10 to the 6th joules, and we divide by mass, which is 60 kilograms, and we multiply by G, which is 9.8. Okay, we get that H is equal to, basically just need to take the answer that we got here, and then we need to divide by 60, and we divide by 9.8, 0.8, and I get 6,407. 6,407. Jesus, that's a huge number, right? So, I think Troy underestimated. Troy, what did you say it was going to be? Like 200 flights of stairs. And a flight of stairs, maybe that's reasonable. Maybe if a flight of stairs, if a flight has about 80 steps in it, you know. Anyway, but you're right. It took a lot. This is a height of this many meters. Now, really, what you need to do now. That's meters. That's a lot of meters. So now you need to divide by the height of the step. And the step is going to have a height of like 10 centimeters, right? So it's actually probably going to be like 64,000 steps total, probably. However, we assumed that our bodies were 100% efficient in converting the food energy into work. The actual efficiency is about 25%. So the work you do as you burn off the sundae is only about 225 kilocalories. The remaining 75% is transferred to the surroundings as heat. and you actually only have to climb about a quarter of this, okay? So the reality is that you really just kind of need to multiply this by a factor of about 25%, okay? Because when we do exercise, a lot of the work that we do actually just leaves the system in the form of heat, pretty much, because it heats our body up and stuff like that, right? So you only really need to burn off a quarter of what you eat in terms of actual, like, you know what I mean? So, anyway, it is, by the way, if you divide this by 4, you get about 1,600, which the book points out is about a mile. You'd have to climb about a mile of steps. Whoa, did I make a mistake? I didn't make a mistake. Oh, the number of steps, that's what you got. Oh, I get it now, okay. True, if they had a larger mass, exactly, you wouldn't have to climb as much because it takes a lot more energy to lift up, like, just to be extreme here. So 60 kilograms, what is it? 60 kilograms is like, that's light. That's like a kid, isn't it? I think when I was the lightest that I've ever been, I think I weighed 75 kilograms. And that's like 160 or something like that. 60 kilograms is like 130 pounds. My God, that is so small. I guess it's not that small for a woman, but it's definitely really small for a man. But anyway, yeah, you're right that if you weigh more, you don't have to do as much. You just gotta, get out there and do some work. Anyway, okay, we gotta stop. We're 8 minutes over. There are a few more example problems here, and you're welcome to review them. We'll go over them at the beginning of class next time. And that's it. I don't know how much more we have in this chapter. Yeah, it's quite a bit more, actually. So we'll have a whole nother day of lecture on this chapter. You have an exam next week, yeah. No, you don't need to remember that. They're just saying that, like, when you're trying to think about how much work you need to do, you only need to, it's just a statement. All right, stopping there. Thanks, everyone.